All right, in this video, we are covering 3.2, which is the Tuesday 115 section, which is all about determining empirical and molecular formulas. Okay, building on some of the math that we used in 3.1, and then we will continue with another conversion factor in 3.3 tomorrow when we learn about molarity. Okay. So we've introduced the idea of empirical and molecular formulas way back in chapter 1. We had addressed the fact that an empirical formula is the simplest ratio of the elements that are present in a molecule or a compound, right? And the molecular formula actually tells us the true number of everything that's present. And these things are important because the elemental makeup, right, determines their identity. And in 3.1, we were given a formula, and we could determine the mass, right? The formula mass, that's what 3.1, a big chunk of that is all about. And then we could use our conversion factors to find moles or to find atoms if we used Avogadro's number. But what 3.2 is all about is answering that question, what if the formula is unknown? Even if we don't know the chemical formula, we can get some serious information just by using mass measurements. And the first tool that we use in that pursuit is called percent composition. And percent composition, which is a percent by mass, and you'll sometimes even just see it called percent by mass or mass percent. They all mean the same thing, percent composition of each element in a compound, which is super easy to measure. You just take grams of that element over grams of the compound, and then you multiply it by 100 to get a percent. So if we take an incredibly easy example, right? Take a 10-gram sample of a hydrocarbon, which means it's just made up of hydrogen and carbon. Okay. And we want to find the mass percents here. Okay. What percentage hydrogen? Okay. 2.5 grams of hydrogen there over 10 grams of the compound multiplied by 100, 25%. And then you see the math for carbon, or you could do it by subtracting from 100 as well, right? 100 minus 25. What's left? 75%. That must be just from the carbon, because we know that those two are what are making up our compound. Okay? That is an overly simple example. That's not something you would expect to see on homework or a test. So if we jump to the next slide and look at a more realistic example, this would give you an idea of what you could anticipate. Okay? Analysis of a 12.04 gram sample of a liquid. We don't know what the formula is, but we know that it has carbon, it has hydrogen, and it has nitrogen. Okay. Tells us we have 7.34 grams of carbon, 1.85 grams of hydrogen, 2.85 grams of nitrogen. What is the percent composition of each element in the compound? Okay. That would be a fair homework question. Right. How do I do it? I take each of those numbers, divide them by 12.04, and multiply by 100 to get a percent. Always paying attention to significant figures, okay, of which we will only have 3 in this situation in the final answer, because each of these numbers have 3 sig figs to begin with. Okay. So you can practice that on your own from slide 32 here. You should get a final answer of 61.0% carbon, 15.4% hydrogen, and 23.7% nitrogen. Okay. So not hard to do if you have the figures that are given to you, right? Then there's another way to do it as well, and that's using the formula mass, another idea that we talked about in chapter 2 and in 3.1. If we know what the formula mass is already, and we know what the formula is, we can determine the percent composition that way. Okay? So if we take ammonia, NH3, okay, you can calculate the formula mass. We know how to do that from 3.1, right? Take the 1 nitrogen multiplied by its atomic mass, 14.01. Take the 3 hydrogens, multiply them by 1.008, atomic mass of hydrogen. Add those together, you get 17.03. Then to find your percent nitrogen or your percent hydrogen, right, just take their respective masses, divide it by the overall molecular mass, multiply it by 100 to get a percent. And it doesn't matter if you're thinking about it on the scale of atomic mass units or on the scale of grams per mole, right, molar mass. You calculate it the same way because those units will end up canceling one another. And you can double check yourself at the end, after you do that math, it should add up to 100%, right? Sometimes it might be 100.1 or 99.9, depending on rounding, but that's a way to check yourself and make sure you did the question correctly. Okay. So on slide 34 here, we have example B. Something else you can practice on your own. I'll upload a separate video showing how to solve this problem. As the mass percentage of iron, okay, in Fe2O3. How do I do that? Well, first I have to solve for the formula mass. Okay? So I take iron, there are 2 of them, so I go 2 times the molar mass of iron. Oxygen, 3 of them multiplied by the molar mass of oxygen, add those up together, that gives me my formula mass. And then I'm asked about the mass percentage of iron, which is all of the iron that's present. Okay? So I take the mass of the 2 irons divided by the total formula mass, and you should get a final answer of 69.9% iron in Fe2O3. So you might be starting to realize that this is a powerful tool. If we know the chemical formula of a substance, we can determine the percent composition. And that's building towards this world of determining empirical formulas. Okay? If we can get the masses of the constituent elements that make up a compound, we can determine its empirical formula. Okay? Remembering that this empirical formula represents relative numbers. We're not just taking these masses and adding them together, right? It's relative numbers, the simplest ratio of the atoms that are in a substance. The simplest, and I should say, to be even more specific, whole number ratio, because we're going to see in a couple of slides where that's important. The simplest whole number ratio of the atoms that are present in a compound. Okay. So how do we do that? We got an important slide coming up here yet. Number 38, slide 38. This tells you the steps to determining an empirical formula. Okay. We're given masses of all the elements that make this compound up. We take those masses, then we use the atomic masses that we get from the periodic table to convert those values to moles, which we did back in 3.1. Make sure you check out that video if that sounds unfamiliar. Then we take those new numbers, which are with the unit of moles, and we divide them by whatever number has the smallest number of moles, okay? Because that's giving us the relative numbers to one another. And then after we do that, if any of those new numbers aren't an integer, right, a whole number, then we have to multiply by a number to give the smallest whole number ratio. So if we ended up with something being like 2.5, for example, then we would multiply everything by 2 to make everything a whole number. Okay? Because these are relative numbers, not masses. Okay? So know those steps. Right? Have a star here next to slide 38. Convert masses to moles, divide by the smallest number of moles, convert to a whole number ratio if necessary. So let's check out an example. Okay? We've got a hydrocarbon again. Compound is determined to have 1.71 grams of hydrogen and 0.287 grams of hydrogen. 1.71 grams of carbon, 0.287 grams of hydrogen. I take those numbers individually. I convert them from grams to moles, which I can always do. You're going to do that conversion 1,000 times by the end of the semester, right? You use the atomic mass to convert from grams to moles by dividing by the atomic mass. Okay. After you do that, right, you're going to get 0.142 moles of carbon and 0.284 moles of hydrogen. So that's after step 1, just converting them to moles. And if you stopped there, right, then your empirical formula would be C 0.142, right, hydrogen 0.284, which if you ever submit that as an answer on a test, then I'm just going to drop you from the course automatically. Because you should even know by now, this early on, you're never going to see C 0.124, H 0.284, right? It just doesn't exist. And that's why step 2 is necessary. Okay? We have to divide all the numbers by whatever was the smallest, which in this case is 0.142. So that's what's going on down here, right? 0.142 goes in the denominator in each situation. Okay? So something's always going to end up as 1, at least off the bat, which is carbon in this case. And then hydrogen, right? 0.248 divided by 0.12, CH2. The 2 is just a little bit cut off on this slide. Okay? And that's it. We have a whole number ratio already, 1 carbon to 2 hydrogens. So the last step isn't necessary. We have established the empirical formula. Keeping in mind, right, that this is the simplest ratio that exists. CH2 doesn't exist, but like C2H4 does exist. Okay, this is just the empirical formula, the simplest ratio of the two. It may or may not be the molecular formula, which we'll discuss in just a little bit. So that brings us to another example here. Okay, a compound is found to determine, or is determined to contain 5.31 grams of chlorine and 8.40 grams of oxygen. Okay. And I'm taking my time here to do another example, so you can imagine it's probably kind of important, right, to know how to do this. I've got 5.31 grams of chlorine. I've got 8.40 grams of oxygen. So I set up my conversion factors. I'm using dimensional analysis. And I'm converting from grams to moles in each case. So I want grams of chlorine to go away, so it's going in the denominator there. Grams of oxygen here. I use their respective atomic masses from the periodic table. Okay. So that rounds to 16 for oxygen, right? 15.999, and chlorine is 35.45. And that is the atomic mass. So that's grams in 1 mole of each of those. So you plug both of those in the calculator, and what you end up with is 0.150 moles of Cl and 0.525 moles of oxygen. And again, I'm not submitting my answer as Cl 0.150, 0.525. I divide both of them by whatever is the smallest, which we're now back to a first grade level question. What's smaller, 0.15 or 0.52? Hopefully you never mess that up. Dividing both of these by 0.150. And after I do that, I get 1 chlorine, right? That's pretty obvious. But 0.525 divided by 1.5, okay, is 3.5 oxygen. So this is an example of where that second step is necessary, right? I can't stop and say ClO 3.5. That's not a proper empirical formula, because an empirical formula is the simplest whole number ratio. So the last step tells me, right, okay, how do I get 3.5 into a whole number? I have to multiply it by some sort of integer. So I multiply everything by 2. And the final answer here is Cl2O7, keeping in mind that those should be subscripts, Cl2O7. Now, all you're going to have to worry about in my course, at least, is if you get a 0.5, you're going to need to multiply by 2. You might occasionally get like a 0.33, so you need to multiply by 3, or a 0.25, so you need to multiply by 4. That'll be as hard as they get. Very easy to figure out how to make those whole numbers. If you end up with like a 0.99 or a 0.02, those are close enough. You just round them to the nearest whole number. Right? We don't have to worry about that, because as we get into harder examples, it's not always going to be perfect like this. So if you get a 0.99, a 0.98, 0.01, a 0.02, you just round those to the nearest whole number. But if you end up with like a 0.82, how do I make that a hard number or a whole number, right? Chances are you just messed up the math somewhere, so go back and double check it. So you'll have the 0.5s like this, 0.33s, 0.25s, but they should be obvious how to quickly convert that into a whole number. Hopefully that makes sense. Okay. So that's calculating in empirical formula. Okay. Second example, and this slide is just going to tell you about what I just said verbally, how to convert that into a whole number ratio, give us Cl2O7. Okay. And then we have a summary slide right here. Okay. The whole strategy for what to do. Take your masses, convert them to moles, divide by the lowest number to get your ratio, and then if that ratio isn't a whole number already, convert to the whole number ratio to get your empirical formula. Okay. Which ties back to percent composition next, because as you're going to see, everything in chapter 3 kind of builds on itself. So we're repeating these ideas in different types of applications, just like we're now using those mole conversions from 3.1 for a different application. Yep. So we can also determine empirical formula from percent composition. How do I do that, right? There's a whole bunch of strategies. And before we even talk about the rules, I'll show you what the question would look like. Okay. Bacterial fermentation of grain produce ethanol, forms a gas with percent composition of 27.29% carbon and 72.71% oxygen. And it asks us to find the empirical formula, because now those are percentages, whereas previously we were working with grams. Right? So what do I do in that situation? No big deal, right? The new rule, number 1 here, is just assume that you have 100 grams. And I'm not going to tell you what to do. You can assume whatever number you want, right? You can assume 43, you can assume a billion, whatever you want. You can assume 0.1. But the reason it's easiest to just assume that you're working with 100 grams is because then you just take those percentages and change percentage to grams. And then after that, notice rules 2, 3, and 4 are the same exact rules as what we had before. So as soon as you convert those bad boys, right, by assuming 100 grams, then it's the same exact approach. It's just an extension of what we've done before. So I take those numbers. If I assume 100 grams, then 27.29% carbon just becomes 27.29 grams of carbon. Then I convert to moles, divide by the lowest number of moles, and then boom, I get my empirical formula, CO2, which you may have already known as a byproduct of fermentation. 2 different ways to find empirical formulas that really aren't different at all. Just if you're given percentages, assume 100 grams so that they become mass measurements. Okay. So hopefully that makes sense as well. We finish by determining molecular formulas. Okay. Whereas the empirical formula is the relative number in the simplest whole number ratio, right? The molecular formula tells us absolute numbers, right? The actual amounts that are present. And in order to determine that, I have to be given the molar mass. Yep. So that's another thing to have down in your notes, right? If all you're given is percent composition or mass measurements and you're not given the molar mass, then you can't actually determine the molecular formula for certain. Okay. So it would be a fool's task. But if you are given the molecular mass, then you can determine the molecular formula. Okay. And we do that by taking the molecular mass divided by the empirical mass, and that'll tell us how many formula units per molecule. Okay. And really what you're thinking about here, and this is going to be a little bit sloppy, so I apologize, is we're solving for an empirical formula. So you can think about it like A sub X, B sub Y. And that's an empirical formula. What we have to figure out is, right, how many of those empirical formulas go in to the molecular formula. And then we just distribute that N through. Okay, so if it was CO2, but 2 of our empirical formulas went into the molecular formula, then it would be C2O4. And you just multiply each subscript by that factor. So it would be A X times N be y times n. Yeah, and this will probably be easier to see when we do another example. So for this example, we're told a compound has an empirical formula of CH2O, which is actually the empirical formula of any carbohydrate that exists in the human body. That's where the name comes from, your chemistry fun fact of the day, right? CH2O, carbon and water, carbon, hydrate, carbohydrate, and CH2O. That's the empirical formula. And we're given the molecular mass of 180 atomic mass units. So what I have to do is figure out, right, for this CH2O, what is the empirical mass? So I have carbon, I've got one of those multiplied by its atomic mass, 12.01, right? I have hydrogen, two of those times its atomic mass. And then I've got the oxygen, only one of them multiplied by its atomic mass. Ooh. And all of those numbers are in AMU. For the sake of rounding and to make the significant figures easier, the math easier, I add those three together, and I'm just going to round it to 30 AMU, right? Should be 30.017, sorry, 027. We'll just round it to 30. 30 AMU is my empirical mass. So now I take my 180, that is my molecular mass. I divide it by 30, and that gives me a factor of 6. Okay. So now to get my empirical formula, or sorry, my molecular formula, I take my CH2O and I multiply everything by 6, every single subscript, and my final answer is something you've probably heard of already, C6H12O6. Okay. So that's how you figure out that factor to multiply everything by. You still find the empirical formula in the exact same way. Okay. And all of that math is shown right here. I figured it was probably a little more beneficial to explain exactly what's going on and how you have to calculate that 30. So 3.2 finishes with what I have as example C here, and it ties everything from the video together. We're given percent compositions, so I have to assume 100 grams and convert all those numbers to grams. Then I have to convert them to moles, divide by the lowest number of moles to get the empirical formula first, and then use the molecular formula to determine the molecular, or sorry, use the molecular mass to determine the molecular formula. So everything from 3.2, all these ideas are tied together just with example C right here. This video has gone on long enough, so I will upload a separate video showing how to solve this one, but I recommend that you practice that one on your own time because that is the perfect way to assess whether or not you're familiar with everything from 3.2, because we'll continue to build on those ideas for the rest of chapter 3 and again in chapter 4.